Good afternoon, everyone. My name is Pen So. I come from TU Munich. Today, I want to talk about my work, which is about the Android malware detection and categorization. In my work, I use a graph neural network to prepare the features. Here we call that is the representation learning. I cooperate my work with Claudia Eckert. She's also from the TU Munich and also the Apostolis Terrace. He is from the Delft University of Technology from the Netherlands. Right now, there are many applications which influenced by the malicious behaviors. So we call that one is the malicious behavior, malicious code, malicious application, and also malicious package. From the capacity reports in last year, about it, in total we have like the 5 million new applications affected by malicious behavior. I mean, which installed by the malicious behavior or malicious applications. Among them, around 156,000 new mobile applications are bank tourists, and also around 20,000 new mobile repositories. And also, in 2019, we also have the report which says that nearly every 7 seconds there is a new released malicious application, and also around 10,000 per day. I mean, the 10,000 malicious samples per day. And in total, in 2019, we got like the 80 million new malicious application for Android device. In this situation, of course, there are many works so far to do Android malware detection based on the different features. Here, many works based on the Android permission. They use the different permission features to say that to check this application is belong to the malicious application and that one is belong to the benign application. Except that, there are also another works which use the Android API code to detect the behavior, I mean the malicious behavior and benign behavior of the different applications. But here we can see no matter of the permission-based or API-based works, both of them use a string like the permission, like the API, the name of the API call, to detect the malware, to detect the malware behaviors. If we use some way to how to say it, to private use the stream, what could be happened? Here, if we use like the string obfuscation, we use a string encryption to encrypt the strings like the permission on the name of the API. What could be happened? Of course, we cannot use the permission-based way to detect our malware behaviors, malicious behaviors, yeah. Except the string obfuscation, we also have another obfuscation technologies, like the class encryption, string reflection, travel obfuscation. The difference between the travel obfuscation and the string encryption is, for the travel obfuscation, we only affect the string in the application, like the name, like the permission name, but for the travel, we didn't consider about the barcode. Barcode is also composed by the many strings. Yeah, we also have another combination of the simple obfuscation technology, like the travel plus string encryption plus reflection plus the class encryption. So this is one point. If we use obfuscation, of course, some methodology cannot be worked. On the other hand, with the increase of the complexity of the applications, we also need to consider the structure of the applications to detect the malicious behaviors. On this topic, there are also another works like the DORI-OL, which use static analysis to get the control flow graph, and then use graph kernel embedding methodology to get the subgraph features, and then put this feature into the classification system, and then we got the result about the benign application or malicious application. Except that, we also have another works like the Adigio and also Manis. the basic idea is also very similar. We use the reduced version instruction and use the one hot embedding to embed each basic block, each function into the embedding, and then put into the machine learning based classification system and then get the result. On the other hand, we also use another work. The name is Jamie, which also use the control flow graph to detect the code similarity. But here, left side is the control flow graph and also the embedding. The point here, the user, I mean, the work of the Jamie, they use many people, I mean, they use a fixed feature like the number of the call, the number of the instruction, and also the number of the offspring. This is a very, how to say, the simplified way to embedding the basic block. Compared another work, our solution is a graph embedding GE, which uses the control flow graph and also the trainable instruction for the barcode. This is our architecture. We have the application, we get the control function called graph, and also the OP code embedding, function embedding, and the graph embedding. And then we can get the features, and then get this feature into the MLP-based classifier, and then we get our result. Yeah, for the first step, we use the Android guide to get the control flow graph, which is very similar with the Adagio and the Manis. We use the OP code embedding to convert our OP code into the vector. Here, we also mentioned why we didn't consider the operand, because, for example, in the move instruction, we have the different operand, but we use the specific symbol to replace all of the mass address on the different registers. In this case, we get the same embedding for different instruction. And also for the invoke instruction, we also have a different type of the OP code. This is the reason, I mean, we think just use the OP code, we can also get the semantic of the instruction. After that, we use the word embedding to convert the OP code into a vector. After OP code, we also have the function embedding, which embeds all of the instructions, the basic block, into a vector. For the function embedding, we also use the two methodologies. The first one is the weighted meaning, and then the other one is the SRF invective function embedding. SRF is a simple but very useful sentence embedding from the natural language technique. After the function embedding, we get the vector of each node in the function call graph, and then we can consider each node of the each node has the vector from the function embedding, and then we should consider how to convert the whole graph into a vector with the graph embedding. After that, we can put here graph embedding. We can put our vector into the MLP system and get the malware classification, binary malware classification, and also malware categorization. Here we compared our work with another works like the Adagio, the Rambin, and the Jordan Martin. From here we can see no matter use the RF embedding, function embedding, or main embedding, we get more than like the 19.8 and 19.7 accuracy. Yeah, we get the best one here. Except that we also get the very good recall curves here. Except the normal situation, we also consider different hub parameters. We test our framework on different learning rate. Here we can see use 0.001, we get more than 19.98% AUC. And also we also test with different training approach, we also get the different result for the malware detection. Here, I mean, actually after 12 approach, we get the more than 19.98% result. We also test on the for the different n-hop neighbor, which is useful thing in the graph embedding. We can see we use a different number of the hop neighbors, we get a different result. We also test on the obfuscate application. Here we can see our framework gets more than 1993% for the class encryption and also more than 19.8 accuracy for the string encryption. This is our rock figure. Last but not least, we also text about the categorization, malware categorization on the ramping dataset. We can see for the top 6 class family, malware family, we get also more than 19% accuracy. Okay, thanks. If you have any question, just tell me and I will answer.